Draw the graph resulting from each transformation. Label the invariant points. The 2 in front of f of x means multiply all the y values of the graph by 2. In other words, we are stretching the graph vertically about the x-axis by a scale factor of 2. Begin by multiplying all of the y values by 2. Here we have plotted the new points and connected the dots to complete the graph. Invariant points are points that do not change position in a transformation. In a vertical stretch about the x-axis, the invariant point lies directly on the x-axis. The invariant point for this stretch is 3, 0. Recall that we are doing example D from the given question. The horizontal stretch factor is the reciprocal of the number inside the function. The half inside the function means multiply all the x values of the graph by 2. In other words, we are stretching the graph horizontally about the y-axis by a scale factor of 2. Here we began by multiplying all of the x values by 2, and then we plotted the points. Once we have connected the dots, we're going to figure out the invariant points. In a horizontal stretch about the y-axis, the invariant point lies directly on the y-axis. Here, the invariant point for the stretch is 0, 2. Here we're doing part A. The negative in front of the function means multiply all the y values of the graph by -1. In other words, we are reflecting the graph about the x-axis. Here we multiplied all of the y values by -1, plotted them on the graph, and joined them. In a reflection about the x-axis, the invariant point lies directly on the x-axis. The invariant point for this reflection is 3, 0. Now we're doing example B. The negative inside the function means multiply all the x values of the graph by -1. In other words, we are reflecting the graph about the y-axis. Here we multiplied all of the x values by -1, plotted the points, and combined them. In a reflection about the y-axis, the invariant point lies directly on the y-axis. The invariant point for this reflection is 0, -2. Here we're doing example C. X equals f of y represents an inverse graph. Swap the x and y values of each point on the graph. This will reflect the graph across the line y equals x. Here we swap the x and y coordinates, plotted them, and joined them together. In a reflection about the line y equals x, the invariant points lie directly on the line. This transformation has 2 invariant points, -4, -4, and -2, -2. A transformation of the form y equals f of x plus k is called a vertical translation. Y equals f of x plus 3 will move the graph up 3 units. Here we added 3 to the y coordinates in order to move the graph 3 units up. Then we plotted the points and connected them to create the second graph. There are no invariant points in a translation. Every point has a new position. The direction of the motion is opposite to the connecting sign, so the x plus 3 inside the function means translate the graph 3 units left. Here we subtracted 3 from the x coordinate to move the graph 3 units to the left. We plotted the points and connected them to create the second graph. The new function after transformation. We can obtain the transformed function by plugging f of x into the transformation equation. We replace f of x with x squared minus 1 and distribute the 2 inside the bracket. If we stretch the graph vertically by a factor of 2, we get the graph of y equals 2x squared minus 2. When the graph is vertically translated, it passes to the point 2, 0. We drew a dot at this location. As we can see, the second point is translated 3 units up, so the transformation equation becomes y equals f of x plus 3. The point 2, 10 exists on the transformed graph. Plug in 2 for x and 10 for y. We need to evaluate f of 2 before we can continue with our algebraic solution. Use 2 as the input for the original function f of x equals x squared plus 3. Replace f of 2 with 7. Now solve for k. Subtract 7 from both sides of the equation to get k equals 3. Since the transformation equation is y equals f of x plus k, and we know that k equals 3, the equation of the vertical translation is y equals f of x plus 3. A basketball player throws a basketball. The path can be modeled with h of d equals negative 1/9 d minus 4 squared plus 4. Suppose the player moves 2 meters closer to the hoop before making the shot. Determine the equation of the transformed graph, draw the graph, and predict the outcome of the shot. The graph of the equation is shown. The vertex of this graph is at 4, 4. When we apply transformation to a parabola, it is helpful to look at the vertex rather than the player or the ball. If the player moves 2 meters closer to the hoop, then the transformation equation is y equals h d minus 2. Then we plugged in d minus 2 as a function of the equation of the original function. Here we simplified the equation as much as we could, and now we can draw the new graph by horizontally translating it 2 units right. The basketball will likely bounce off the top of the backboard. To find the transformation, let's start with the original function before the player moved. The goal is to transform the old function into the new one. If the old graph is horizontally translated 5 units left, we obtain the new graph, represented in the orange color. As represented by the scale, from -5 to 7, the person moves 12 meters away from the hoop.